All right, so we're still working on some results exercise about the weak topology. So we are starting with proposition 28, which states that if a sequence xn converges weakly toward x, then the sequence xn is bounded for the usual norm. Furthermore, you have that the norm of the limit x is less than this limit inf. All right, so we are going to prove. Okay, so let's prove this this result. So we've seen that since the sequence converges weakly, we have that for all phi in the dual space. So the dual space is the form, the set of the continuous linear forms on E. We have that phi of xn converges toward phi of x. So this is in K. All right, so what do we have? Well, it follows that so the sequence, so phi of xn is bounded in K. Which means that this quantity is finite. And so this is indexed by n, and this is for all continuous linear applications from E into K. Okay, look at that. Now, if I consider here xn as an application, so I can consider xn as an application from E prime to K, and at every phi in E prime it associates the value phi of xn. So if I look at xn like that, I can apply the uniform boundedness principle so the uniform boundedness principle works with, as an hypothesis, I have a uniform bound for each fixed phi. I have a subborn over n, and the conclusion is that instead of considering for each phi, I obtain a bound on the norm operator of Xn. So from the uniform boundedness principle, I deduce that so instead of phi, I get rid of my phi and I obtain this is the norm of the operator. So as an operator, so here it's the norm from but so we've seen that no, so what's the meaning of that is as an operator norm, this is the okay. Okay, but we've seen that exactly here, this thing is exactly the same that the norm of Xn. So here is the norm on E. We've seen that. That's a result. Okay. So finally, I obtain that. I obtain that. This was the first part of the results, meaning that if Xn converges weakly, then the norm of Xn is bounded. So Xn is bounded in E for the usual norm. All right. So next, what do we want? We want also that. So how are we going to obtain that? So let's work again. So we know that so we have this thing. And so if I look at for all phi such that we have that Okay, now I take the limit inf. So taking the in both sides, what we obtain? We obtain, so phi of xn as n goes to infinity converges to phi of x. So the limit inf of phi of xn is phi of x. So we obtain that phi of x is less than this. All right. But here it's for all phi with norm less than 1. So again, taking the sup here, we have also that. I just take the same expression, but with the sup now. Oh, sorry. And this is equal to norm of x. So finally, and that's the result. So next we are considering this exercise. That is, if xn converges toward x weakly, and if phi n converges toward phi in the dual, then phi n of xn converges toward phi of x in K. So let's have a look at this solution. It's quite short. So we are just going to write the difference phi of x minus phi n of xn. And so I introduce here phi of xn. Now I use the property of the norm. And finally, we have that this thing holds. And now we're good because phi of xn converges to phi of x, and phi n converges to phi in the dual. So we're done with the exercise. Okay, so so next we have the following results. That is, so when E is of finite dimension, in fact, the weak topology and the usual topology are the same. Okay, so if some U is an open set for one of the topologies, is also an open set for the other topology. All right, so yeah, let's think about that. All right, so let's prove this this result. So we know already that if if U is an open set for the weak topology, then U is an open set for the usual topology, where tau denotes the usual topology on E. Okay, so what we need to prove is the other way around. So conversely, assume that U belongs to tau. So tau is the usual topology. We are going to prove that. So we want to prove that U belongs to the weak topology. So to do that, let X be some point in U, so we want to prove that there exists an open set V, so it's a weak open set, so in such that X belongs to V and this is included in U. So if I prove that, if I find such a V, I'm done. Okay. So yeah, let's try to find such a V. So to do that, what we know is, since U is an open set for the usual topology, there exists some positive constant R such that the ball, so in E of center X and radius R, is included in U. So now let's try to define our open set V. So to do that, we are now going to use the fact that E is of finite dimension. So let's E1, E2, En be a basis of E, and such that for all I in 1n, we have the norm of EI is 1. All right. So next, we define an application phi I from E to K, such that at X, it associates phi I of X equals Xi, where where so the x1 till xn are the coefficients of x in the basis. Okay, so without loss of generality, because we're working on a finite set and all the norms are equivalent. So for the purpose of the proof, we can assume that the norm of x is the norm 1. So norm of x is the sum from I equals 1 to n of xi. Okay. So what can I do with that? So you can check that. You can check that phi I is in the dual set. Okay. Okay. So let's define our V now. So I will define V as the intersection of, so this is the ball in K from some epsilon. Okay, then, so V writes as a finite intersection of reciprocal images of balls in K, of open balls in K. So B is the, as the usual notation is that B is an open set and is the open ball, and this is the open ball in K of center xi and of radius epsilon. So then V belongs to the weak topology, and X belongs to V. So if we prove that V is included in U, that's enough. So to do that, it is sufficient to prove that V is actually included in the ball of center X and radius R. So let Y belongs to E, or better, let's Y belong to V. So if I write the norm of Y minus X, okay, this is by definition okay, but this is and so by definition, this is less than epsilon. So this is less than n epsilon. Okay, if Y belongs to V, then phi I of Y belongs to the ball of center xi and epsilon. So this is less than epsilon. So finally, let epsilon be, or let epsilon such that, so choosing finally choosing epsilon less than r divided by n gives that norm of y minus x is less than r, which in turn implies that v is included in u. And we're done. So next we have the interesting following result. That is, so if E now is infinite dimensional, then the sphere, which is a closed set for the usual topology, is not a closed set for sigma E prime, meaning that in particular, when E is finite, the weak topology and the usual topology are the same, but that's not the case when E is infinite dimensional. For example, the sphere is not a closed set for the weak topology. So sorry, the mic was off. So we are going to prove that that in fact the closure of S in the weak topology is the closed ball, the closed unit ball. Okay, so in particular, we have that the closure of S is not equal to S, and which means that S is not a closed set. Okay, so we only need to prove to solve the exercise, we only need, in fact, to prove that the closure of S is not equal to S, but we are going to prove a little bit more. That is, in fact, we are going to prove that the closure of S is the closed unit ball. And so to start, let's pick up X node such that the norm of X node is less than 1. And we will see that, in fact, X node belongs to the closure. So, in fact, this is sufficient to prove that the sphere is not closed, because if X node is in the unit ball, the open unit ball, so if the norm of X node is less than 1, it does not belong to the sphere. So if you prove that X node belongs to the closure of the sphere, this means that the closure of the sphere is strictly greater than the sphere, and that proves that S bar is not a closed set. Okay, so if you want to prove that X node is in the closure of S, so let V be an open set of the weak topology such that X node belongs to V. And so we want to prove that V, the intersection between V and the sphere, is not the empty set. Okay, so let's do that. Okay, so since V is an open set that contains X node, I know that there exists, so let phi 1, phi n, such that the intersection between from I equals 1 to n of phi I minus 1 of phi I x node so it's a ball, and radius epsilon is included in V. So phi I, so my phi I belongs, of course, to E prime. Yeah. So I recall that since V is an open set which contains X node, I can find some open sets such that X node belongs to the intersection of open sets that write phi I minus 1 of Ui. And so I can find also a ball such that of radius epsilon, so phi I of X node belongs to my open set Ui. So I can write that here. Okay. All right. And so here also I need to define, of course, epsilon. Okay. So next, there exists a Y such that for all I, phi I of Y equals 0. If not, so here we use the fact that E is infinite dimensional. So if not, if such a Y will not exist, then this would imply that E is finite, is of finite dimension, because if not, you can construct an application from E into a finite dimensional set, and that's not possible. So we can such a Y exists because E is of infinite dimensional dimension. All right, now let's consider this application. I consider the application that at T associates this function in R. So first note that let's call it G. So it's from R to R. And note that G of 0 equals norm of x0. This is less than 1. And as T goes to infinity, I have that G of T equals plus infinity. So, and furthermore, G is continuous. So there exists T node such that G of T node equals 1. So meaning that X node plus T0 Y equals 1. So this one belongs to the sphere. But if I look at my phi I, phi I of x node plus t node y equals phi I of x node plus t0 phi I of y, and this is 0. So this is phi I of x node. Therefore, x0 plus t0y belongs to V, because it belongs to okay. So I have x0 x node plus t node belongs to V, and the intersection of belongs to the intersection of V and the sphere, and so that's it. So what we did prove that. So we just proved that x node belongs to S bar. Okay, meaning that the ball is included in S bar. So this implies that S, which implies that S is not closed. All right, so we have a little bit more because in fact, so now in fact, the closure, the closed ball is a closed set in the weak topology, because it writes as so, because this is the, by definition, but again I can write it as such that the supremum, so the phi are in E prime of such that, because norm of x is that. Okay, so finally I can write that BE, so B closed, yeah, Okay, so finally I can write it. So is an intersection of closed sets. So we have that. So we proved that BCO1 and since this is a closed set, this implies that you know that the closure is the smallest closed set which contains S. So we have that finally BC01 equals as well. Okay, so to end this session, I'll let you think about this exercise. So the unit ball is not an open set for the weak topology. Okay, so why is that? So assume that's the case. Assume that B belongs to the weak topology. So then the complementary, it's so by definition is that. So if B is open, then the complementary is closed by definition. Of or for, let's say for. Okay, but then what? Then S. Okay, let's then. So then S equals it's BC, and this is a closed set. With the intersection of B, and this is the complementary. So if this is closed, so if this is closed, we obtain that is closed, which is a contradiction. So yeah, the unit ball is not an open set for the weak topology.